In Chapter 14, we'll be looking at organic compounds that have oxygen, halogen, or sulfur in the structure. Here we're seeing a picture of gypsy moth, which can be problematic to trees. And these moths can contain a sex pheromone called disparler. So disparler is a sex pheromone of the gypsy moth, which is an epoxide, and it can be used to control the spread of gypsy moth caterpillars. In general, an alcohol is an organic compound that has a carbon group, which is the R, and it is attached to an OH group, which is our alcohol. So generally that is what the structure of an alcohol is. And we also have an ether, which is an oxygen that is sandwiched between two carbons. And some structures that we have examples of are ethanol, that has the CH2CH3 group, or we have diethyl ether. The general structure of an alkyl halide is a carbon-containing compound with a halogen, which is fluorine, chlorine, bromine, or iodine. And we also have a thiol, which looks like an alcohol, except it has a sulfur present. So we might see a thiol in 2-mercaptolmethylfuran, which gives the aroma of coffee. And we have the ether here. And in sevoflurane, the general anesthetic, we have an ether, as well as all of those CF bonds are our alkyl halides. In the structure of paclitaxel, which is also known as Taxol, we can see different alcohol groups here. And this little cyclic one here is an ether. Taxol, if you're not familiar, is a complex anti-cancer agent that's active against ovarian, breast, and even some lung tumors. They originally did some biological studies with Taxol that were carried out with natural material isolated from the bark of the Pacific yew tree, but stripping the bark killed the trees. And so now instead, Taxol can be synthesized using plant cell fermentation, which is much better for the plants. So instead of killing these great trees, we can synthesize the compound in the labs. Okay, so on this slide, we're asked to label hydroxyl groups, sulfhydryl groups, halogens, and ethers. And then we're going to look at the alcohols in salmeterol, and then to explain which is not part of an alcohol. Okay, so in chondrocholy, which is isolated from red seaweed, this is a halogen. So I'm going to circle the halogens in blue, and then circle ethers in red. So the halogens are in blue. In this next compound, which is the onion-like odor in human sweat, this is 3-methyl-3-sulfanyl-1-hexanol. I have an alcohol, which I'll do in green. And this is a thiol, which I'll circle in orange. All right, so we have an alcohol here in salmeterol, a couple of them actually. All right, and then the question number 2 says, which OH group in salmeterol is not part of an alcohol, and explain. And if I had to guess why this book wants to list this one as not an alcohol, it's because it's on an aromatic alcohol. And we just learned in the last chapter, it can also be called phenol. So this compound, salmeterol, is used to dilate airways and can be used in the treatment of asthma. If we're looking at different classifications of alcohols, they're classified by the number of carbons that they're bonded to. In the first one, the COH has bonds to one other carbon group. So this is a primary alcohol. This one has 2 carbon groups that's attached to the COH, so this is secondary. And with 3 groups, this is tertiary. There's no way that we can have a quaternary alcohol. And if we look at an example here, a secondary alcohol is shown in blue, and that has this carbon that is bonded to 2 other carbons. The alcohol in green is a tertiary alcohol, and this one is bonded to 3 other carbons, so that's 1, 2, 3. And in the pinkish, reddish, orange there is a primary alcohol, which is only bonded to 1 other carbon. So if we're to go and classify these alcohols, I look at the COH, which is this guy right here. That one's bonded to only 1 other carbon, so this is a primary alcohol, while this carbon is bonded to carbon 1 and 2 here. This is a secondary alcohol. So you can take a look at this practice problem for these 2 compounds. This is linalool and lavandulol, which are both isolated from lavender. So this linalool, we have this COH right here, And I count 1, 2, 3 carbons. So this is the tertiary alcohol. This one right here is only connected to one other carbon, so this is a primary alcohol. Alcohols have a net dipole because of the oxygen is electronegative, plus it has those electron lone pairs. So the net dipole goes towards the electron lone pairs as we see those two polar bonds. And we also can see that alcohols also have intermolecular hydrogen bonding. So in a CH3OH, this is methanol. In methanol, with the CH3OH bond, the oxygen lone pairs can hydrogen bond with the hydrogen on another alcohol group, and those can hydrogen bond together and so exhibit the intermolecular hydrogen bonding. Alcohols are polar because oxygen is much more electronegative. And they can be water soluble if the number of carbons divided by the number of nitrogens plus oxygen is less than 4. Their melting and boiling points are higher than alkanes. And that's due to the hydrogen bonding and strong intermolecular forces. So butane has the melting point of -138 C and the boiling point of -0.5 degrees C. And I replace one carbon with an OH group to give us propanol, and now my melting point is -127, and the boiling point jumps almost 100 degrees to 97 degrees Celsius. So propanol is going to have strong intermolecular forces from hydrogen bonding capabilities versus butane. So in order to determine if propanol is water soluble, we add up the number of carbons, which is 3, divided by the number of oxygens, which is 1, plus nitrogens, which is 0. This is less than 4, so this is water soluble. To name alcohols, you want to find the longest carbon chain that actually has the OH group as part of the carbon chain. Then you want to number the chain to give the OH the lowest number, and then apply all of our other nomenclature rules. If OH is in a ring, the OH is going to be number 1, and then all the other substituents will follow to give the lowest overall numbering. So first we're going to find the longest chain with the alcohol. Here's our longest carbon chain. The alcohol is going to get the lowest numbering, so this is 3. We have a methyl group at 5, so this will be 5-methyl-3-hexanol. When we're looking at the cyclic structure, alcohol is going to get 1. And if I number clockwise here, the second carbon will have the substituent. So this will be 2-methyl-cyclohexanol. We don't need to list 1 in front of the alcohol. In a cyclic structure, the 1 is assumed. If you have multiple alcohol groups, I find my carbon chain here is 5, so that'll be pentane. This will be 4-methyl-2,3-pentane-diol. So we have a practice problem here. Find the longest carbon chain. I'm going to number to give my alcohol the lowest numbering. And then list alphabetically. The ethyl group at 5 will come first. So this will be 5-ethyl, 6-methyl-3-nonanol. So that's going to be a nonane, and then the ol is for the alcohol. And then here we're asked to draw the structure of 2-ethyl-3-methyl-cyclohexanol. I'm going to start with the parent. That's cyclohexane, an alcohol. I have an ethyl group at 2, methyl at 3. Ethanol is an interesting alcohol that is present in alcoholic beverages. Ethanol can be created from yeast fermentation. It uses glucose or sugar, which has the formula C6H12O6 that can come from grapes. There's yeast that is tossed into the mixture, and that can ferment in these barrels, creating ethanol plus carbon dioxide gas. So the structure of ethanol is CH3CH2OH. So the fermentation of the carbohydrates in grains and grapes is performed. This requires yeast. So the yeast contains the enzymes to convert glucose into ethanol. Ethanol can also be used as a common laboratory solvent and is also an additive in gasoline because it is good for combustion. Methanol is also an interesting alcohol. It has one carbon, so this is a CH3OH. That is a solvent in organic labs and also can be a starting material for the synthesis of plastic. This is actually a toxic compound if consumed. Back in the days of prohibition, people would try to distill their own alcohol and they would leave some methanol behind in the process. And so a lot of people became blind or even died. Ingesting 15 milliliters can cause blindness, and 100 milliliters can cause death. 2-propanol is a solvent that you may not know as 2-propanol, but this is also called isopropyl alcohol, and that's the major component in rubbing alcohol. It's used to clean skin before medical procedures and sterilization. And glycerol, which is our final interesting alcohol here, has 3 carbons and 3 alcohol groups. This is used in lotion, liquid soap, shaving cream, and is also an additive in candy, some prepared foods, because it binds well to water and helps to retain moisture. Starch and cellulose are carbohydrates that have many alcohol groups. Starch is in seeds and roots of plants, so we'll find it in wheat, rice, and potatoes, which most of us consume, while cellulose is found in tree trunks and plant stems, so we might see these in wood, cotton, and flaxseed. So cellulose is connected differently than starch is, so amylose is one type of starch, and you can see these groups all kind of chain down and link down together, and those can be hydrolyzed to give us glucose for energy, and cellulose can be hydrolyzed as well. This one goes straight across, but our bodies don't contain the right enzymes to hydrolyze cellulose. There are many reactions that can be done with alcohols, one of them being elimination reactions. And in this reaction, parts of the starting materials are lost and a new multiple bond is formed. So we're going to lose water in a dehydration reaction and form an alkene. So we form the alkene via the loss of water. And this is done using sulfuric acid, and oftentimes heat accompanies this reaction as well. In ethanol, which is the structure drawn here, we're going to lose this water and form ethene. And the byproduct in these reactions is the H2O that was lost. Sulfuric acid plus cyclohexanol, we're going to get our 6-membered ring and form a double bond. This is cyclohexene. And plus water. Oftentimes with dehydration reactions, you can form more than one possible alkene. So if we're looking at 2-butanol here, we have carbon 1 and carbon 2. We can eliminate from either side. So the first alkene you might look at forming is 1-butene, where the alkene forms between carbon 1 and 2. Or with the same structure, you can dehydrate between carbon 2 and carbon 3 to give 2-butene. And 2-butene is the major product. Because we have 2 carbons that are coming off of the double bond. Versus here, there's only 1 carbon coming off of the double bond. So having a more substituted alkene is better. If you have a choice when you're eliminating water, your product will prefer the one that gives you more substituted alkenes or more groups coming off of the carbon-carbon double bond. If we look at this reaction here, we're going to use H2SO4 and throw in some heat. And I'm going to see what elimination products can occur. And usually you have your alcohol. I'm going to have an H here. I'll call that HA. We have a hydrogen here. We'll call HB. And you usually want to look to the carbon on either side of that alcohol. So if this is the carbon in question, it's the hydrogen on either side of that can be eliminated. If I do the reaction with HA, that's going to form a double bond here. Just draw the dotted line there. we'll get rid of the alcohol and form that double bond. And then if I go to do it with HB, I'm going to form a double bond there and eliminate the alcohol. And my double bond will form here. So if I look at this, there's 2 carbon groups coming off of this one. So this one is di-substituted. This one has 1, 2, 3 groups. This is tri-substituted. So this one is the major product because there's more groups coming off of there. In these practice problems, we're going to look at drawing the products that result after a dehydration reaction. In this alcohol here, this is symmetric, so we don't have to worry about multiple products. We're going to look for the hydrogen on the adjacent carbon, and this is what is getting eliminated. So that's where my double bond is going to form right there. And there's my double bond. Here I have a benzene. There's only one product possible because I have a primary alcohol. So I'm going to take in H if I just remove that here. If it helps, you can draw it out in stick form or the skeletal form. This is what we're looking at. This is the carbon here. I'm going to eliminate a hydrogen from here. That's the water that's getting eliminated. And there's my double bond. So because it was a primary alcohol, we only have one possible product. Another reaction we can do is an oxidation reaction, and this results in an increase in the number of CO bonds or a decrease in the number of CH bonds.